All right. So hi, Musa. Hi, everybody who may be then watching online. So today is a kind of side lecture. It's not part of the course, but so the goal today is to describe action angle variables on open dense subsets in coadjoint orbits of UN. And this also goes under the name of the Gelfand Zetlin integrable systems. And here usually it's an interesting story, right? So we give here the spelling in Latin alphabet, but so the name of Zeitlin, it has many spellings, and I guess one of the reasons is the fact that the spelling in Cyrillic, it has this letter ts, which kind of can be whatever. There are many transliterations, Z, TS, C, and so in principle there are many spellings in Latin alphabet of that name. So that's the Cyrillic spelling. Maybe before we go into this discussion, just to compare. So let's say if we have T, an n-dimensional torus, T is Lie algebra, and we have delta inside T star, which is Gelfand. So such that M delta omega mu from M delta to T star is the corresponding toric manifold. So then if one considers a preimage of the interior of delta, it is isomorphic to the product of this interior and the torus. So if we denote the corresponding coordinates, lambda 1, lambda n, theta 1, theta n, the two form on M delta has the following form. And so that's something like that we want to see for coadjoint orbits of UN. However, note coadjoint orbits of UN are not toric in general. So some of them are toric, but most of them are not toric. And so we want a similar construction, but for symplectic manifolds which are not toric. So we'll see in different kind of instances, different facets where this difference will manifest itself. Okay, so let me recall some stuff about UN coadjoint orbits. So we choose G equal to UN. The Lie algebra can be identified with skew Hermitian matrices, or the imaginary unit times Hermitian matrices. The dual is identified with Hermitian n by n matrices. The pairing is the imaginary part of the trace. The coadjoint action is simply the action by conjugation. Coadjoint orbits are, of course, orbits of conjugation, and it's convenient. We know that every Hermitian matrix can be diagonalized by conjugation by unitary matrices. So it is convenient to choose representatives which are diagonal, and moreover, we can choose the eigenvalues to be ordered, for instance, in the decreasing order, or sometimes people prefer increasing order. So this means that actually the conjoint orbit, this is the set of Hermitian matrices with fixed eigenvalues. Now, just to recall the two form. So we'll need the two form on omega. And sorry, I probably again mixed up notation and signs, who knows? So we have the projection from the group to O lambda, which is mapping the group element to the G conjugate of lambda. And the two form is like this. It is minus D of imaginary part of trace, and here lambda times the Maurer-Cartan form, or it is often convenient to apply this D, and this would give this. Right. Okay, so that's basically the question. Here is this two form, and the question is how to find this type of coordinates, this type of expression for this two form. So for that, we'll need several gadgets, and I'll start with the first gadget, which is called the Gelfand Zetlin map. And it looks as follows. So this is a map from Hermitian matrices to some space Rn. So we have our Hermitian matrix. So these are some matrix elements. and I'll map it into a so-called triangular tableau. So the first row will simply be those ordered eigenvalues, which I will redenote lambda 1n, lambda 2n, lambda nn. So that's because n is the size of the matrix. And then what we do, we cut the upper left corner. Sometimes one cuts the down right corner, doesn't matter, but let's fix the upper left corner. So this is again a Hermitian matrix. Let me call it psi n minus 1. It again has eigenvalues. We denote them lambda n minus 1, 1, lambda n minus 1, n minus 1. And we continue doing it until we reach the top left corner. So here the matrix is 1 by 1. And this is simply equal to psi 1, 1. So I'm not sure whether it will work for me geometrically. So this is supposed to be a triangular tableau, but that's of course just a way of writing a map from Hermitian matrices to some vector space. So this is the GZ map from Hn. And if you count the number of the resulting number of eigenvalues, this will be R to the power n times n plus 1 over 2. So that's how it looks like. Okay, so there are the following facts about this map. First of all, those lambdas satisfy the interlacing inequalities. So the interlacing inequalities look as follows. So lambda ki greater or equal to lambda k minus 1 I, and greater or equal to lambda k I plus 1. So this is some instance of linear algebra. So I guess you people probably know how to prove it. By the way, Musa, do you know how to prove such things?
I guess by some conjugation to some standard form. I don't know.
Think about it. Yeah, I mean, of course, this is like first year linear algebra, but I mean, yeah. So it's an interesting question. You basically need to use the right definition of eigenvalues. So the like minimax or max mean principle. That's what one should use, and then the inequalities will become obvious. So they form zigzags. Those inequalities, they form zigzags between the rows of the triangular tableau. So now the second remark, we can consider Hn reg. Sorry. So we can consider Hn reg, and let's define it that the set of xi's for which all inequalities in the triangular tableau are strict. Right? So here they are non-strict typically, but suppose that all of them in all of the tableau are strict. So it turns out that then the functions on that set lambda ki are smooth on this set. And otherwise, they have singularities. So maybe a simple exercise. Check it for n equal 2. And furthermore, assume that I've chosen lambda 1 strictly bigger than lambda 2 and so on, strictly bigger than lambda n. So I suppose I chose lambda 1, lambda 2, lambda n, and distinct real numbers. So then it turns out that O lambda intersection with Hn reg is open and dense in a lambda. So it's a good subset. And finally, one more linear algebra fact. If we take the image of Hermitian matrices under the Gelfand Zetlin map, we obtain exactly the cone defined by interlacing inequalities. In other words, whatever lambdas satisfy those inequalities, you can get them from there is a Hermitian matrix which has that set of eigenvalues for the matrix and for submatrices. So this is also it's kind of it's all easy stuff, some kind of elementary linear algebra. Maybe now a little bit of notation. So we have those corners of our Hermitian matrix. So these are elements in HK. So top left K by K corner of Xi, and Xi K is diagonalized with eigenvalues lambda K by some unitary K by K matrices GK. And if lambda K's are all distinct, then this GK is defined modular multiplication on the right by a diagonal matrix, right? Right, so in principle, GKs are not uniquely defined, but and these are the traces, right? Okay, very good. Up to now, it was all very easy and sort of trivial. So now there is something which is really a little bit complicated, interesting, difficult. And this goes under the name of theme torus action. So first of all, let me introduce a notation now of capital N to be 1 plus 2 plus so on plus n minus 1. And this is, of course, n times n minus 1 over 2. And we define the torus of the corresponding dimension, Tn. And we're going to define its action on H and reg preserving all lambda. So in fact, on each all lambda, which let's say preserving all lambda intersection H and reg. So for each all lambda, we're gonna have an action of Tn on the intersection of all lambda with H and reg. And for most coadjoint orbits, if all the eigenvalues lambda 1, lambda n are distinct, this will be a torus action on an open dense subset. So that's already one element of what we want. Okay, so right, this Tn will be structured like a one-dimensional torus, that is a circle, times two-dimensional torus, times three-dimensional torus, and so on, up to torus of dimension n minus 1. And I will first define the actions separately. So suppose we have Tk equal to Z1 Zk, an element of Tk. And so I will be acting by this thing on my Hermitian matrix, which is called zeta. So remember that zeta has those corners, and the corners are diagonalized by unitary matrices Gk. And so I define matrices Vk by this funny formula. Right. And I'll define matrices capital Vk, which are n by n matrices, where we have the block Vk, upper left corner, 1, down here, and 0. So this is in UK, and this is in UN. Right. So this is a capital Vk. Okay, so far so good. It looks somewhat strange. So now a surprising, I think a kind of surprising formula. So Tk acts on zeta by sending it to a conjugate. Sorry. By conjugate by Vk. So first of all, this is a conjugation. And therefore it preserves eigenvalues. And it preserves all lambda. Now, why this is an action of a torus? So maybe we can have a look in a little bit more detail how all this looks like. So let's write our matrices in a block diagonal form. So here we have ZK, and let me denote the other parts by AK, BK, and CK. Right? So that's how it looks like. And well, if you just do the matrix multiplication, what will happen? So you'll see that you have this. So here you're gonna have AK, VK minus 1, VK, BK, sorry, yeah, K. And here CK doesn't change. Okay, so some complicated action. But let's look at this guy, how this guy looks like. Well, this guy looks like this: GK, TK, GK minus 1, GK lambda K, GK minus 1, GK, TK minus 1, GK minus 1. Okay, so those guys cancel out. But now lambda is diagonal, TK is diagonal, therefore TK also cancel out. And so this is simply equal to GK lambda K GK minus 1. And this is actually equal to psi K. So in fact, this action, or whatever, to be action, it doesn't change that upper left corner. Right? And this means that new GK is simply equal to the old GK. This is important because of the following. Suppose you have two elements, T and T prime, and you take a composition. Right? So this is a conjugation with, no, the other way around. With VK, VK prime, psi, right? But what is this? This is VK, VK prime 0, 1, 0. And since GKs are the same, this is GK, TK, TK prime, GK minus 1. So this is really equal to the action of TK, TK prime. Sorry. All right. So we established that this is indeed this funny formula defines a TK action. But moreover, what is kind of surprising those messy actions, so those actions defined by this formula for tori of different dimensions, they actually commute. How could it be? So let me, so I gonna prove this fact and another involved fact, and other things I won't be proving too much today, but this I plan to prove. So claim TK actions on this HN reg commute. Well, wow, how could this possibly happen? Okay, so let me choose K bigger than L, and I will first compute TL acting on TK acting on Xi. So what is it? Well, we know that this is TL acting on VK Xi VK minus 1. But we know that in this matrix, the K by K corner remains the same. And the L by L corner, therefore, is the same as for original matrix. But then this means that not only GK tilde was equal to GK, that's what we saw, we used in the previous argument, but also GL tilde is equal to GL. And this means we actually know what this is. This is VL, VK, Xi, VK minus 1, VL minus 1. These are our definitions of before. Well, that was an easy direction. Now, a complicated direction is as follows. We need to compute TK TL Xi. Okay. So this is equal to, of course, by definition, TK acting on VL Xi VL minus 1. And in particular, so how does this thing look like? So I want to split it now into the left corner is now K by K. And what is standing here, now things do change, right? So this is a conjugate VL Xi K VL minus 1 and some whatever garbage here, but we are not that interested. Okay, so that's how it looks like. Now this guy, right? So this is Xi K tilde, new Xi K. It's equal to VL Xi K VL minus 1. And well, we know it is VL GK lambda K GK minus 1 VL minus 1. So now that's a new So that's the new GK tilde. Now we can continue the calculation. And this is equal to VL tilde, VK tilde, VL, psi, VL minus 1, VK minus 1. And well, now we need to figure out what is VK tilde VL. Well, but we now know what it is, right? It is VL GK conjugation TK GK minus 1 VL minus 1. So that's this VK tilde and times VL. What is it? Well, that's a simple identity. Those VLs cancel out. And we get VL times GK, TK, GK minus 1. And this is VL, VK. And this VL, VK is exactly the same as this VL, VK over there, right? So, wow, as I say, those, I mean, this, to start with, it just doesn't look like an action. And I mean, it sounds very improbable that different TKs commute. But now we just proved it. So here. Right. Okay. So sorry for all these maths, but I thought it's kind of interesting to see how this machinery works. Of course, I just could have stated this proposition, but then you wouldn't see the machinery. And also we'll need it in the next theorem that we're going to actually prove. So after that, we're going to have things that we don't necessarily prove. Okay, here is a theorem. And it's about 40 years ago, due to Gilman and Sternberg. Right. Okay, so there are two statements. There are many more, but let me phrase it in that way. So so the action of the seam torus on O lambda rag, which is O lambda intersection with H and rag, is Hamiltonian. Now assume, to simplify things, that our orbit corresponds to distinct, has n distinct eigenvalues. So then let me have GZ n minus 1, and I'll explain what it is the moment map for this action. So what is GZ minus 1? We have a triangular tableau. And in this triangular tableau, we have the first row. So in this first row stand our eigenvalues. And recall that they are not changed, so they are constants on the coadjoint orbit. So So I'm only taking things which are below the first row, so all the other rows. And that I call GZ n minus 1. In other words, all the numbers which stand in a triangular tableau, in all the other rows but the first row, they constitute a moment map. Maybe I should better say a moment map, because, you know, for a torus section, I can always shift by constant. So here I choose some particular moment map. All right, so you see those two things, those two constructions, they nicely fit together. This strange sim action and the Gelfand Zetlin map, which is a sort of rather naive map. So let me show you the proof of this theorem. So how does it work? So let me choose an element of the Lie algebra of TK. So I will be acting. So let me say tau k is in Lie of TK, and let me denote by xk the element gk tau k gk minus 1 0 0 0, and this is in the Lie algebra of UN. So that's the corresponding element. You know, I just take an infinitesimal action of TK. So, you know, we act by conjugation. This means that basically we go through some UN action, and that's the corresponding element. So I want to compute the contraction of omega with this action, and so I'm computing the contraction of omega with imaginary part trace, and here lambda g minus 1 dg square, and the action is on the left. Okay, so well, we now go for a relatively lengthy calculation. So it's imaginary part of trace, and as usual, I will probably mix up the signs. We'll see. So here lambda, and here will be minus g minus 1 xk g minus 1 dg plus g minus 1 dg g minus 1 xkg. So the first part of the calculation will be tedious but routine. Something interesting will happen in the second part. So now we're just doing a routine. So that's imaginary part of trace. And here I want to isolate xk instead of lambda. So it is g lambda g minus 1 dg g minus 1 minus dg lambda g minus 1 xk. So this is, I'm just rearranging terms, and this is equal to imaginary trace, and here d g lambda g minus 1 times xk. Right. Okay, good. So, but recall that my xk is of this particular form, right? And so this is xi, and xi is of the form xi k, garbage, garbage, garbage. So here the trace is over an n-dimensional space, and I can actually rewrite it as imaginary part of trace, now only of a k-dimensional space, d psi k xk, right? So something interesting starts happening. Now, well, let me substitute imaginary trace k, and I know that psi k is gk lambda k gk minus 1, and xk is gk tau k gk minus 1. All right, still looks very, very messy. And, you know, in a couple of lines from here, we're going to have a very beautiful, very simple expression. At the moment, it's difficult to believe. It's some kind of magic stuff. You know, already this action of the theme torus, that was really very, very improbable, but it worked. So now again, this expression, well, it doesn't look like it's gonna look good. So okay, so let me go ahead. So it will be something like this: gk minus 1 dgk. Now lambda k to k plus d I think I missed somewhere the minus sign, but okay, so be it. So d lambda k tau k and minus lambda k gk minus 1 dgk tau k. Okay, good. So what? Well, this is equal to imaginary part, trace k. And here gk minus 1 dgk. And here actually you have a commutator of lambda k and tau k. But remember, they are both diagonal, whatever they are. So this commutator is simply 0. And the remaining term, possibly with the wrong sign, is d lambda k tau k. And this is d imaginary trace k lambda k. But that's exactly is saying that those lambda k, the row, so the case row, of the GZ tableau is a moment map for the TK action. Up to sign, yeah, the sign, I think I probably messed up. So we've actually proved the theorem of Gilman-Sternberg. So you see, it's a sort of, in some way, not very complicated proof, but in the second part some miracles start happening. I think in principle, if one uses more formalism, perhaps this would come as a more obvious thing. So I made it somewhat calculational, but on the other hand, it's very, very convincing, right? We're just computing it, and that's what comes out. Now let me give you some more remarks and facts. So first of all, one can choose coordinates. Let me call them lambda ki, those we already know, but then the angle coordinates. So these are our actions, and these are our angles. So in other words, coordinates on fibers of the GZ map. And we can do it such that the two form on the orbit, the KKS form, would locally acquire the form so you see, this is not quite guaranteed from the Gilman-Sternberg theorem that we've just proved. So why is that? So so this actually depends. It depends on the choice of angles. And indeed, if you choose different angles, right? Plus possibly some function, maybe of lambdas, right? You can always shift the zero on your fiber, right? Your fiber is isomorphic to a torus, but not canonically isomorphic. You can change the zero by some function of lambda, and this would give omega KKS equal to sum over ki, so this term will be still there, plus some d lambda garbage. So that, so let me just tell you in words how to choose those, or maybe part of the good choice. So we basically need to choose where your thetas are equal to 0. And for that, you notice that n by n symmetric matrices. So the matrices with real entries. So here, psi, ij's, they are all real, is sitting inside Hn. And it turns out that so GZ -1 of some triangular tableau, of course, in the regular part, it intersects sim n in a finite number of points. So I think the cardinality of this set will be 2 to the power n. So basically what you need to do, you need to choose, you need to, yeah, there is a question? Okay.
Anton, did you start an hour ago or something like this?
Yeah, that's true. Is it the wrong time?
No, because
oh my God, because you didn't change time.
I just came now, yeah, but I didn't think about it. We should have discussed it. I didn't even think about it.
Oh, okay, yeah.
Did anybody arrive? Did anybody arrive an hour ago?
Muse.
Just Muse.
Yeah, no, but I mean, but we thought that anyways, it's good to have a recording. Yeah, all my apologies.
Well,
yeah.
So shall we just carry on and you'll record it, you'll post it? I mean,
yes, I think
because you planned your day around it.
Yeah. It's my fault. Yeah, because I thought what's going on, but I thought, you know, this is this special week, who knows? And I thought that we still need a recording.
It's such a shame. Anyway, you will see probably a lot of people arrive in the next 10 minutes.
Probably, yeah. So sorry, people. But then the next 10 minutes is going to be something interesting. So I hope they're going to enjoy. Yeah, my apologies. That's my fault.
It's okay. I guess we'll have to just manage.
Okay, okay.
Right.
So I'm just saying how to choose angle variables for the Gelfand Zetlin system.
Yeah, it's the
Right. So it turns out that those theme tori, they all intersect this space of symmetric matrices in some finite number of points. And actually, there is a way how to choose one of them. So that perhaps I'm not going to explain. But there is a way to choose one of them. So, and that will be the zero of the corresponding theta ki variable. So, and then this garbage term will not be there, and we really get Darboux type coordinates. Okay, so maybe that was one remark. So the other remark, so this Gelfand Zetlin story, I presented it for orbits where all the eigenvalues are different, but it also works for smaller orbits. And let me give you an example. Suppose we take the tableau where two eigenvalues coincide. Then, of course, in the Gelfand Zetlin pattern, so we'll have some kind of triangle where everything is the same. And here there will be lambda 2, 2, lambda 1, 1. So there will be still inequalities like that. Well, so this orbit, so the corresponding orbit is a quotient of U3 by the stabilizer. What's the stabilizer of lambda 1, lambda 1, lambda 3, a diagonal matrix? It is U2 cross U1. So the dimension of O lambda, the real dimension, is 9 minus 4 plus 1 is equal to 4. So this is a real dimension. So here is an exercise. So show that delta described by those inequalities, right? So you have variables which are lambda 1, 1 and lambda 2, 2. So lambda 1 and lambda 2 are fixed once and for all. Sorry, lambda 3. So they're fixed once and for all. And so this describes for you on the plane some kind of polytope, right? So show that this polytope is Gelfand. And the corresponding M delta is isomorphic to CP2. And in fact, U3 mod U2 cross U1 is isomorphic to CP2. So now I want to end with the following example. So that's again G equal to U3. So we have lambda 1 bigger than lambda 2, bigger than lambda 3. And let me denote the elements in the Gelfand Zetlin tableau by X, Y, and Z. So I have 6 inequalities. Let me denote the corresponding polytope by delta lambda. And it turns out it is not Gelfand. So let's look at it. So for that, one efficient way is to look at the vertices. The vertices of that polytope. Just to give you an idea, I will look at a good vertex and at a bad vertex. So for instance, a good vertex is lambda1 is equal to x is equal to z, and y is equal to lambda3. So which means that this, and these inequalities are strict. Are actually equalities. So what happens here, right? What are the corresponding vectors? So x small or equal than lambda1, right? So one of the vectors is -1, 0, 0, right? So that's the vector which corresponds to this inequality. So the vector x equal to z, or x greater or equal than z. So this is this vector. Now, and finally, the third one, y greater or equal than lambda3 is 0, 1, 0. So that's the third one. Now, well, I mean, by inspection, we see this is a basis of Z3, right? So this is a basis of Z3. And so this corner of delta lambda is Gelfand. So, I mean, now it doesn't contradict to be in Gelfand. However, there is one bad corner, which is x equal to lambda2 equal to y. This is because if x and y are equal to lambda2, then necessarily z is also equal to lambda2. Here, we even don't need to analyze the vectors. The problem is we have 1, 2, 3, 4 inequalities, which are actually equalities. And 4 is too many, right? So we have 4 vectors in that 3. It's not a basis, whatever it is, right? There is a linear dependence. So therefore, this polytope is not Gelfand, and this coadjoint orbit. So this coadjoint orbit is actually what? It is O lambda isomorphic to U3 modular what? U1 times U1 times U1. Its dimension is 9 minus 3 times 1 is 6. So those generic 6-dimensional coadjoint orbits of U3, they are not toric manifolds. So we do get those Gelfand Zetlin polytopes. Very interesting, very nice. However, there are no toric manifolds which correspond to them. This means in particular that the action of the sim torus that we defined, it does not extend from the regular set to the whole orbit. Now, one more, yeah.
Does it also mean that the action of the isotopy subgroup is not free?
You mean which one?
In the symplectic reduction.
But you see this. I mean, if we let's put it that way. If we tried to define the symplectic reduction as we did 1 week ago, then the action would have been highly non-free. However, we would not have obtained, like this guy O lambda is not at all obtained by that symplectic reduction. So if you run the symplectic reduction with this polytope, as we did last time, you would obtain something which is not at all smooth.
So presumably this is related to the part of the lecture which we at the beginning, right? Is that
no?
No. Okay.
No, absolutely not. No,
Mm.
exactly the opposite. It connects to the lecture we had last time. So now we are looking, you see, we are looking at this space. We already knew, even forget today's lecture, right? We know that conjugacy classes of Hermitian matrices in Hermitian matrices are coadjoint orbits of UN, and so they are symplectic spaces. In the part of the lecture that unfortunately you would need to look up later on, we constructed the torus section on some open dense subset. And this torus section has a moment map, and I'm now just describing the image of that moment map. That's this polytope described by those inequalities. However, this is not a Gelfand polytope. It just by inspection, you see, I just proved it's not Gelfand. It has a corner which is really a bad corner. In Gelfand polytope in dimension 3, all the corners should be intersections of 3 planes. But this one is an intersection of 4 planes. So that's it. But now I want to show you in a bit more detail what's the difference. So so let me say, to compare. So if we had, suppose if we start with delta Gelfand, right? Sorry. So if we started with delta Gelfand, so and then M delta toric, right? And suppose that alpha in delta is a vertex. And so we have a convex polytope. Something like this. And alpha is a vertex. Then in toric story, we know that mu minus 1 of alpha, right? Delta is the image of the moment map. The pre-image of a vertex is the torus divided by the full torus. In other words, this is a point. So the pre-image of a vertex in a toric manifold is just 1 point. Now let me tell you, in our funny example, what's the pre-image of a vertex? So in our case, so we want to know what is GZ minus 1. So GZ is that map of here. I'm just repeating my story. I have lambda 1, lambda 2, lambda 3. Here we have lambda 2, lambda 2. And here we also have lambda 2. That's the Gelfand Zetlin tableau. So of course, now for those of you who, because of me, missed the most of the lecture, you don't know what it is, but I can say how it looks like. So these are matrices of the following form. So these are Hermitian matrices of this form, such that their eigenvalues are given by lambda 1 bigger than lambda 2, bigger than lambda 3. Well, of course, we know that in the conjugacy class, the trace is an invariant. So therefore, 2 lambda 2 plus C is equal to lambda 2 plus lambda 1 plus lambda 2 plus lambda 3. And C is actually fixed. And then this is a simple linear algebra exercise that the only constraint on A and B is that A squared plus B squared is some constant which depends on lambda 1, lambda 2, lambda 3. So therefore, we actually know how this preimage looks like. So this preimage is isomorphic.
So Anton, sorry to correct. Isn't it correct that you mean on the you missed GZ inverse needs to appear on the right hand side as well?
No.
What you wrote, this set of matrices lambda 2, lambda 2, C
Yeah.
represents the Gelfand Zetlin.
So the preimage of the, you see, the preimage of triangle of a particular tableau lives in H3.
I see. Okay.
Right. So
no, that's okay. In that case, it's okay.
So I'm looking at all the matrices 3 by 3 Hermitian, which have a tableau of this very particular form: lambda 1, lambda 2, lambda 3, lambda 2, lambda 2, lambda 2, where lambdas are fixed. So I choose lambda 1 bigger than lambda 2, bigger than lambda 3. And then I just look at all the matrices which have such a tableau. So, and here they are. That's how they look like. So these are just a complete description of them. So I have these Hermitian matrices of those particular form. And so we have lambda 1 bigger than lambda 2, bigger than lambda 3. So that's the description. Now it turns out that the only interesting condition is this one. And actually, if absolute value of A squared plus absolute value of B squared is a constant, which depends on lambda 1, lambda 2, lambda 3, this matrix we will have exactly that tableau. So that's it. Or it would have eigenvalues lambda 1, lambda 2, lambda 3. So that's and so it turns out that this set of matrices, its topology is S3, right? Because we have two complex numbers, their absolute values squared add up to a constant, so it's S3. Okay, sounds perfect. You see now there is a huge difference, right? So for a corner in a Gelfand space or in a toric manifold, a preimage of a corner is a point. Here, a preimage of a corner is huge, is S3. So an interesting fact, this is a Lagrangian S3. And just to give you an idea, so I gave you an example in very small dimension, but I think the general story of arbitrary dimension, it was only figured out last year by Carshon, Lane, and there is one more collaborator that I don't remember. So this the story of the Gelfand Zetlin map is the story which is developing, and also so we were discussing UN, and so this is the story which was developed by Gilman and Sternberg 40 years ago, and there was a big problem, a big question, how to generalize it to other groups, so especially the symplectic group, and also maybe to exceptional groups. Is their construction independent of the type? And such a construction was only found a couple of years ago by Hoffman and Lane. So actually, so the story that we saw today, it's a classical story, but it has aspects which connect to very, very recent things, to the advances in our understanding of moment maps and symplectic geometry, which date to 1 or 2 years back, and I think it continues to develop. So again, my apologies for kind of yeah, mixing up the time. So I was usually only mixing up signs, but now it was a more serious. Was a more serious thing. I promise for the next time to do it better. And I think we're gonna just very soon, once the Zoom link arrives, so we're gonna post the Zoom recording, so you can basically recover the first part of the lecture. So sorry again about that. So Jude, I'm not quite sure what you mean by next time zone. I mean we probably
we will fix it. We will fix it properly. We'll do it.
Yeah.
I'll make sure they know. It's also I should have thought of this.
No, but I should know. In what sense they should know?
Okay, but I mean the point is that I don't know. Anyway,
No,
it was not taken care of. It's we didn't think of it. It's ironic because it's not very long ago that Switzerland didn't change the time, and they used to have this strange anomaly between France and Switzerland, but now Switzerland adapted to Europe.
Yeah. No, but I'm my apologies. Let me switch off the recording.